Routh criteria. It is an absolute stability, that means which gives just yes or no information of the stability of a particular system. It will not give the complete details of a stability of the system, like it will not give the degree of stability, just it will give the yes or no information related to the stability of a system. So here let us take a transfer function. So standard transfer function s plus z1 into s plus z2 s plus z3 so on divided by s plus p1 s plus p2 s plus p3, like this. So this is a transfer function. In general we will be representing like g of s by 1 plus g of s into h of s. So this is our generalized transfer function. So out of this, the denominator term is called a characteristic equation of the transfer function. So based on the characteristic equation, we will find the stability of a system, whether the poles are lying on left hand side of S plane, or lying on imaginary axis, or lying on right hand side of the S plane. So based on that, we will say whether the system is stable or unstable. So just will give the yes or no information of the stability of a particular system. The advantage of this Routh criteria is we can calculate number of poles lying on the right hand side of the S plane without solving the characteristic equation. Just we are finding the number of poles, how many poles lying on the right hand side and how many poles lying on the imaginary axis, or how many poles lying on the left hand side of the S plane, without solving the characteristic equation by using this Routh criteria method. So here the roots of the characteristic equation are nothing but poles of the transfer function. This is the main point we are taking here. Roots of this characteristic equation are nothing but poles of the transfer function. If the roots of the characteristic equation are lying on the left hand side, that means the poles of the transfer functions are also lying on the left hand side, so that the system will be stable. And another point is number of poles lying on right hand side of S plane. Number of poles lying on right hand side of S plane can be calculated without solving the characteristic equation. Can be calculated without solving the characteristic equation. This is one of the advantage of the Routh criteria. So let us solve the Routh criteria method for finding the stability. So let us take the characteristic equation. Let the characteristic equation is a0 into s power of 4 plus a1 into s power of 3 plus a2 into s power of 2 plus a3 into s power of 1 plus a4 is equal to 0. So let us take the characteristic equation like this. When we are having some necessary and sufficient condition for the Routh criteria, necessary conditions for stability, First one is there should not be any sign changes in the characteristic equation. That is the first necessary condition for Routh criteria. There should not be any sign changes. There should not be any sign changes in the characteristic equation. So either plus or minus, the coefficients of characteristic equation should be having same sign. There should not be any sign changes in the characteristic equation. And the second necessary condition is no coefficient should be missed in the characteristic equation. No coefficient should be missed in the characteristic equation. That means every coefficient has to be present, a0, a1, a2, a3, a4 for all the s power of 4, s power of 3, s power of 2 and s power of 1, like that. So no coefficient should be missed in the characteristic equation. These are the necessary conditions for solving the Routh-Hurwitz criteria stability. And there are sufficient conditions are also exist for them. So we'll see that. Sufficient conditions for Routh-Hurwitz criteria stability. For Routh-Hurwitz criteria. So this sufficient condition will be Routh-Hurwitz criteria. The tabulation has to be satisfied. So for RH criteria, the RH table must be satisfied. RH tabulation, RH Routh-Hurwitz tabulation to be satisfied. So we will form the Routh-Hurwitz tabulation for this Routh-Hurwitz criteria stability. So this is a sufficient condition for that. And here the Routh-Hurwitz tabulation will be like this. All the coefficients we have to write in a column wise: s power of 2, s power of 1, s power of 0. Then we have to write all the coefficients here. S power of 4 we are having a0, and s power of 3 we are having a1, s power of 2 we are having a2, and here a3 and a0. So it is a4. This is a4. Now coming to this 2 coefficient, we have to multiply like this: a1 into a2 minus a0 into a3 divided by a1. So this will be a1 into a2 minus a0 into a3 divided by a1. This is the first coefficient of this. Second coefficient, for the second one, a1 into a4 minus a0 into 0 divided by a1. So that means a1 into a4 minus 0 divided by a1. So it gives us only a4. Only a4 will be there. So we can directly write a4, or we can multiply that one. Next, for this s power of 1, so let me call this as b. Therefore next one, for s power of 1, b into a3 minus a1 into a4 divided by b. This is my next column. b into a3 minus a1 into a4 divided by b. And here there is no coefficient left, so therefore I can keep 0. Next one, here b into a4 divided by b will gives us only a4. So after completing this Routh-Hurwitz criteria tabulation, we have to observe the first column of the RH table. So the conditions are here. There should not be, for the stability, there should not be any sign changes in the first column of the above tabulation. So there should not be any sign changes. There should not be any sign changes. There should not be any sign changes in the first column. In the first column of RH tabulation. COLVA, column of RH tabulation. Then the system can be called as stable system. So in the first column there should not be any sign changes. This is the first column. So if you observe the first column, there should not be any sign changes in the RH tabulation. Then we can say that the system is stable. If there are number of sign changes existing in the first column, then that number of poles are lying on the right side of S plane, number of sign changes in the first column is equal to number of poles lying on RHS side, number of poles lying on right hand side of S plane, number of poles lying on the right hand side of S plane. So this is really regarding Routh-Hurwitz criteria, stability, necessary and sufficient conditions.